Hello everyone, and today we will be talking about logic gates. And in order to understand how digital logic is performed, first we must understand what are electronic gates made of. Because while these gates exist in theory, they do not necessarily exist in electronics. We must make them using this, a transistor. A transistor is a very interesting component. It's pretty much the equivalent of an electronic switch. It's called a semiconductor, and it has these three leads: uh, collector, base, and emitter. And what these do is the collector pulls in electricity, and when there's power running through the base, it emits the power on the other side. So this can be used to make things like AND gates, NAND gates, OR gates, and then using what's called functional completeness, we can use those gates to build up other gates. So now before we get into using these components to make gates, I'm going to talk about functional completeness. So functional completeness is the idea that using only one or two gates, gates such as NAND or NOR, one can create any other logic gate that exists. So as an example, let's use NOR to create a NAND gate. So we have so let's figure this problem out by hand. So if we make the truth table for the NAND gate, it would be something like this. So you have input A, B, and your output. So you have 1, 1, 0, 0, 0, 1, 0, 1. So a NAND gate, when A and B are 1, is going to be 0. But then for the rest of them, because NAND is not AND, this is going to be 1. So now let's look at the NOR gate in comparison. So you have your output, and 1, 1, 1, 0, 0, 1, 0, 0. So neither this nor that. So if anything is on, this is off. Okay. So what we can see is we want to say that if both of them are on, it's 0. So what we could do to make this NAND gate is first make an AND gate out of the ORs, or the NORs. Now this right here is an AND gate, but in order to make this into a NAND gate, all we have to do is negate the output. So we could throw it through another NOR. Because the NOR, when it receives only one value, will negate the output. So, and this would be a NAND gate. So, if we can make either NAND or NOR using transistors, then we can make any gate using transistors. So I am going to build the NAND gate and be right back. So here we have the finished NAND gate circuit, and just to prove it, we can try out the truth table on it. So let's see, 1 and 1. So 1, 1, that's off, but then the other combinations, so if only A is on, the LED's on. If only B is on, the LED's on, and if neither of them are on, the LED is on. So, as I said earlier with functional completeness, because we can make a NAND gate out of these transistors, that means we can make any gate out of these transistors, which is how they make gates such as these. So these are XOR gates that I purchased just for this project. Let me take them out. Now, these XOR gates are going to be really useful because the next thing I'm going to show is how to make a binary adder using logic gates, and I'm going to do it with these integrated circuits. So I have this, which is a XOR gate, and I do have the integrated circuit for an AND gate. Let's, as a reminder, go over how to make an adder. So when you're first we'll go over how to make a half adder. When you're adding two numbers together, the truth table looks something like this. So you have your output and your carry out. So we'll just fill in this table, and then using what we know, we'll figure out what logic gates we need. So what this is telling me is that I'm going to need an XOR gate connected to the output and an AND gate connected to the carryout. And using only two gates, we can make what's called a half adder. And it's pretty simple. You have A and B, and you just have one AND gate and an XOR gate. Which I'm trying to draw correctly because I always get it wrong. Something like this. Then all you need to do is take the inputs and then this can be the carry out, this can be the output. So when you combine these two, the truth tables of the AND gate and the XOR gate together, you do get a half adder. So I will build the half adder first and be right back. So here we have the completed circuit. Red is carry out. It's connected to the XOR gate right here, or the exclusive OR. And the blue is the, actually, that's the other way around. The red is the output because it's connected to the XOR gate, and the blue is the carry out bit. So we can test this. So if we have one in, the output's on. If we have two in, the output's on. But if we have them both on, just the carry out is on. So this is how a computer adds numbers. I will next make a full adder, and a full adder is this exact thing, except it takes another input, the carry bit. And the carry bit is, well, obviously this circuit isn't going to work for what we want to do, but the carry bit is yet another input. So you can use the carry bit to chain together adders, because there's the carry out. So then if you carry in the carry out, then you can add bigger binary numbers together. So the truth table for this would look something like this. So let's say 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1. 0, 0, 1. So this is the completed truth table. So this would be 0, 0. This would be a 1 on the output. This would be a 1 on the carry out, because there are two numbers we are adding. So this is the edge case kind of right here that matters. This is very important right here what we're doing. This one, there's a 1 on the output and a 1 on the carry out. So that's going to be the main difference that we're going to need to worry about. Then this one would be 1, 0, 1, 0, 1. So what we're looking for is the exact number of inputs we have. So on 3 inputs, 3 true values, we're going to output a 1 in the output and a 1 in the carry out. But for the rest of the inputs, it kind of works the same way as the half adder does. So I will draw the diagram next, and then I will make it up in the electronic circuit. So now that we've seen how to make a half adder on the last part, I'm going to black box it, which means I'm going to just make it a thing, and we're not going to look at it again. So the half adder component has an A and a B, and gives your output and your carry out. So then, how are we going to use this half adder to make a full adder? And the way is pretty interesting. What you do is you take 2 half adders, which is why they're called half adders. And you just chain them together. So you have your A, your B, and your C. All you do is your A and your B go into here. This comes over here. Your C goes into the bottom of this half hour adder, and then we're going to take the carry out bits from both these half adders, and we're going to OR them. And this will give us a full adder. So that's relatively easy, and the good thing about this is with a full adder you can chain these together infinitely to add any size binary number you want together. So this is extremely useful. This is what they use to make arithmetic units inside CPUs, at least for the adding part, and also a half adder or a full adder can handle subtraction as well, depending on the system you're using for storing negative numbers. But that is a topic for that you will learn in someone else's video. So thank you for your time.